Assalamualaikum. We have completed half wave rectification, so now we are ready to continue with full wave rectifiers. Okay, so we will be looking at two architecture. The first is full wave bridge rectifier, which consists of diodes, and the second one is a center tap transformer rectifier, which makes use of a transformer. Full wave rectification. So as I mentioned in the first slide, in the first video part 1, if we have a time varying input signal, okay, when we rectify, we want to change it from an alternating current to a signal that is only in one direction, either only positive or only negative. So in this case, we have here an example where we have it only in positive, but for full wave rectification, the negative cycle is reflected to become as part of the signal in the positive domain. So you don't lose any signals here, but instead it all becomes unidirectional, making it just one direction without omitting the negative cycle. So the rectification process can be done in full without cancelling the other half cycle by using a full wave rectifier circuit. If it had been a half wave rectifier circuit, we would have cancelled the other half cycle. Full wave rectification produces greater average DC value. Remember, for our half wave rectification, the average DC value was 0.318 of the maximum voltage, but here we have it at 0.636. So since the area is now doubled, the average DC value is also doubled. So half wave, it was 0.318 of the maximum voltage, and full wave would be double, so it would be 0.636 VM. Full wave rectification. Now this is the bridge network, and for our example here, we are using ideal diodes to make things simple. So what this full wave full bridge rectifier, the full wave bridge rectifier does is, you have an input voltage Vin, which is a sinusoidal signal, and then you have V out, which is the voltage across this resistor, okay, where it becomes just in the positive area. So you have your 4 diodes, D1, D2, D3, D4, and it will selectively turn on based on whether it is the positive cycle or the negative cycle. Okay. So a full wave rectifier bridge network consists of 4 diodes that are connected in a bridge configuration, just like a bridge here. Okay. During the positive input cycle, the diodes D2 and D3 are on. Diodes D2, so positive cycle means the direction of current flow is from the top. It goes to D2. It won't go to D1 because D1 would be reverse bias. It goes to D2, and then it goes to R, and then it goes to D3, and then it goes back to the negative terminal. So we've drawn it here. So D2 and D3 are represented by short circuits, and D1 and D4 are represented by open circuits. Okay. During the negative cycle, meaning this is the negative cycle, now Vin flows from the bottom terminal here. It goes to D4, which is now become short circuit, but D3 is open circuit. It goes to R, giving the value of V out, and then it goes to D1 through D1, which is represented by a short circuit, back to the top terminal. So V out in both ways will have the current entering the top terminal positive. So both positive and negative cycle are shown to be positive V out. Okay, since the diodes are ideal, the load voltage V out is equals to V in. If we do a KVL around here, you're gonna have minus V in, okay, minus V in plus V out is equals to 0. Okay. So what happens if the bridge network now has diode that are represented by an approximate silicon diode model, meaning that it's no longer an ideal diode, but instead we have here a diode that is represented by its forward voltage when it turns on. So if we are considering the positive cycle, then we know that the diode D2 and D3 will turn on. I think this was this D3 just now. So if we do a KVL around this loop, okay, minus V in plus 0.7 plus V out plus 0.7 equals to 0, we can find an expression relating V out to V in that includes the expression of the forward voltages. So let's have a try. So if I were to do a KVL, it get minus V in plus 0.7 plus V out plus 0.7 equals to 0. So V out is going to be equals to V in minus twice of 0.7. Okay, in general. So if we're considering the maximum voltage, so now if we're considering the maximum voltage here, V out max, okay, V out max occurs when V in is max, which is Vm minus 2 times the forward voltages, and the DC voltage, okay, the average DC value is going to be 0.636 times the maximum voltage of the output, which is Vm minus 2 times forward voltages. And for situations where Vm is really larger than the forward voltage, the following equation can be applied for the average value with a relatively high level of accuracy, which is just 0.636 Vm. This is shown by the last example when we changed the input voltage from 20 volts to 200 volts in the previous video. Okay, and we saw that the change on the average DC value was reduced from 3.5% to 0.35%. So if it's 0.35% of a change, we can safely ignore it, because it doesn't seem to make a large effect on the average DC value. Okay, so now let's have a look at the peak inverse voltage. It's the same thing. Again, when the diode is supposed to be in reverse bias, it is not supposed to break down, so we need to know the required voltage, okay, the peak inverse voltage, the required peak inverse voltage of each diode, so that it doesn't break down. And this can be determined using the peak of the positive region of the input signal. So from the configuration, we say that PIV must be greater than Vm for full wave bridge rectifier. How do we know that? Let's do a KVL here. Okay, so we replace what is supposed to be forward bias to be short circuits. Okay, Vm is V equal to V out is equals to Vm, which is supposed to be the maximum voltage that is supposed to take. Okay, so now we're considering just the ideal diode. Okay, and we know that for the ideal diode, V out is equals to V in. So when V in is maximum, which is Vm, V out is also maximum. And when we want to consider the peak inverse voltage, this was our diode. Okay, the negative terminal, we take that as the positive for the PIV voltage, and the other terminal as the negative. So we can do a KVL here, and I'm going to get minus PIV, okay, plus Vm is equals to 0. Therefore, the peak inverse voltage should be at least Vm, and to be safe, it should be much bigger than that. Okay, right. So now we're done with the full wave bridge rectifier. Now let's have a look at the center tapped transformer. Okay, now a center tapped transformer, okay, full wave rectifier is a type of rectifier which uses a center tapped transformer. So this is a center tapped transformer and two diodes to convert the complete AC signal into DC signal. Now, why should we consider using a center tap transformer in the first place? Remember when I showed the introduction of a power supply? Okay, when you want to do AC to DC, the voltage that comes from AC would most probably already be coming from a transformer. Okay, so having a center tapped transformer full wave rectifier makes sense because that interface to AC is already from a transformer. Okay, going back to here, the center tapped full wave rectifier is made up of an AC source. Okay, we have an AC source which is input voltage, a center tap transformer, two diodes, and a load resistor. Okay, the same thing for your full wave bridge rectifier. You had R with V out as the voltage across it. This is the same thing as well. Okay, so before we go on into the center tapped transformer full wave rectifier, let's just do some revision. You may or you may have not heard of center tap transformer from other courses. Don't worry, it's you'll be facing a lot of designs where there will be other parts or modules that we have never seen before later on when you go on in your life dealing with technologies. So what is a transformer? Okay, transformers are electrical devices used to transfer electrical energy by mutual induction, where you can have a V in here, and by mutual induction you have V out here. Okay, so mutual induction is the process by which a coil of wire, primary winding, magnetically induces a voltage into another coil, which is the secondary winding here. So you have a primary winding here, and this comes from the AC source. Okay, it's transferred to a different part, which is induced into the secondary winding, located in close proximity to it. Okay, you can have a step up transformer, you can have a step down transformer. So a center tap transformer. Okay, what is a center transformer? When an additional wire is connected across the exact middle of the secondary winding of a transformer, it is known as a center tapped transformer. The center becomes the ground. It divides the input AC signal. Okay, let's say the AC signal is VP. It divides it into two parts, VA and VB. The upper part of the secondary winding, so this is the primary winding and this is the secondary winding. The upper part of the secondary winding produces a voltage V1, and the lower part of the secondary winding produces a negative voltage V2. The voltages V1 and V2 are equal in magnitude but opposite in direction. Opposite in the sense that, you know, you have if this is going to be a common ground, okay, if this is the common ground, then you have VA here, okay, and VB here. You have a positive with respect to this terminal below here. But if this is ground, then VB here is going to be the opposite polarity, opposite direction to VA. Okay, so this is a center tapped transformer, simply where you have one voltage here, and you can transfer the voltage. You can produce the voltage at another part. For VP, you can produce it VA at one part and VB at another part. Okay, so if you have your NA and NP, okay, where VA is equals to NA over NP times VP, if the number of winding in the secondary winding of part A is the same as the primary winding here, you will get VA to be equals to VP. Alright, now back to the world of white background. So back to the world of full wave rectification. The function of the center tapped transformer here is to establish the same input signal across each section of the secondary of the transformer. So if I have V in here of an AC source, Okay, the center tap transformer will also produce V-in at the top section and V-in at the bottom section. Now this is going to be ground, okay, but because V-in at the top and the bottom section are voltage across, so it's going to be plus with respect to the ground, and here the plus the higher potential is going to be at the ground with respect to this positive terminal D2. So when this is V-in and it is the positive cycle, okay, during the positive input cycle, V-in is produced at the top section, okay, and because the diode at the top section positive terminal is at the positive is in the direction of positive current flow, therefore the top diode, which is diode D1, is on, but diode D2 is off because this is going to be negative with respect to ground, or rather we can say that the lower potential of V-in is going to be connected to the positive terminal of D2, therefore D2 is off. And if we consider the voltage across V out, across R is V out, then doing a KVL along this flow, you will get V out to be equals to V-in, and the maximum voltage here is going to be the maximum voltage of V out is going to happen when V-in is also maximum. Okay, so during the negative input cycle, now when the cycle is negative, okay, the top part, okay, is also going to be negative, just like the negative cycle, with the lower potential, okay, going to be connected to the positive terminal, so it's going to be in the opposite direction of current flow, so this one is going to be open circuit. But the bottom section, okay, from this ground, it will give a positive a higher potential to the positive terminal, so this one will become a short circuit, and at this point the bottom section will turn on. So D2 is on and D1 is off. And when you do an average value, just like the full wave bridge rectifier, because this value is graph dependent, it's not on what circuit is producing it, so it's going to be the same because you have here double of the half cycle, so it's going to be 0.636 Vm. But what about the peak inverse voltage? Now this peak inverse voltage is going to be slightly different from the bridge wave rectifier. Okay. Now if I consider the peak inverse voltage, it is going to be okay, I will need to consider, okay, let's consider the bottom part here. If I were to have a peak inverse voltage, okay, the peak inverse voltage, this is D2, right? Okay, and then we have our coil here. Okay, so peak inverse voltage, and the voltage across V out when I do peak inverse voltage has to be the maximum, but in this case here, this value at this bottom part of the winding is already Vm. So if we do a KVL around this plot, around this loop, okay, I'm gonna get negative Vm, negative Vm, so negative Vm minus Vm plus PIV is going to be equals to 0. So PIV is actually Vm plus Vm, which is equals to 2 Vm. So here you see that for the center tap transformer, even though we just use 2 diodes, okay, you're gonna get this the same value of the average DC value, which is 0.636 Vm, but the peak inverse voltage is now doubled. So the diode that you place in a center tap transformer has to be able to have a higher rating. But what's the advantage of using a center tap transformer over the bridge rectifier? One is that you have a ground here, the common ground is settled, and you're going to be connected to a transformer anyway because you're going to be communicating with AC. Okay, so let's do an example. We have a bridge network. Now let's do something to the bridge network, because we said that the center tap transformer has 2 diodes, right? So now why can't we have a bridge network consisting of 2 diodes? So let's build a bridge network with 2 diodes. So given the bridge network, determine output waveform and calculate output DC level and required PIV. So you have to do 3 things here. One is to find the output waveform with respect to the V in versus time here, sinusoidal wave, and then calculate the output DC level, which is going to be VC is equals to 0.636 times the maximum voltage of the output signal, and the required peak inverse voltage, which we have to do, which we'll have to treat one of this as a as an open circuit, label it as PIV, and do a KVL to see what the relationship is to the maximum value. And we are asked to assume that the diode is ideal. Alright, so with the diagram, with the circuit given, we will redraw it so that we will label where we want to name the resistors, the different 2 kilo ohm resistors. They're all 2 kilo ohm, R out, R1 and R2. And then we have the 2 diodes, which I will call D1 and D2, and the given voltages of V in and V out. Okay. Okay. So I hope I've not confused between V in and V1. Yeah? So this is V in. So the positive cycle of V in, this is V in. Okay. When it is the positive cycle, D1 will turn on, and D2 will be an open circuit, but the resistors R out, R1 and R2 are resistors, so they don't go forward biased or reverse biased, so they just obey Ohm's law as long as there is a complete circuit linking them to the voltage source. So we have here D1 short circuit, and then we have R out and R1, and then R out and R1 is actually in series, okay, because this one is open circuit. So in this connection here, R out and R1, there's only R out and R1 because D2 is an open circuit. So R out and R1 is in series, and if I indicate this node with this orange dot here, okay, so R out and R1 together, they are in parallel with R2. So R out and R1 is in series, so meaning that they have the same current, and because they have the same resistance, therefore they have the same voltage drop. So V1 is equals to V out. Okay, so if I do a KVL here, V1 is equals to V out. Okay, if I do a KVL here, I'm going to have negative V in plus V out plus V in, plus V1, which is V out. So I'm going to have V out is actually equals to half of V in. And at maximum values, we know that it is given that V in is 10 volts, so V out is 5 volts. So now we will consider the negative cycle. Oops. Okay. So now with the negative cycle, D1 will be open circuit, and D2 will be short circuit. Okay. Now, when D1 is open circuit, at this middle point here between R out and R2, it will be only R out and R2 that is connected, which means R out and R2 is going to be in series with each other. Okay, at this point here, there are no other connection because this is an open circuit. D1 is non-existent in this case. But at this node, okay, between R out and R1 is going to also be connected to this connection which is the short circuit of D2, so will then be connected to the positive terminal of the supply V in. So R out and R1 is no longer in series because there is a third connection here, but R out and R2 is going to be in series. So we will draw this between these 2 points, these 2 nodes of these green nodes. Okay, I have just added these green nodes here so that you see how to redraw it. So we have R1 in parallel with the combination of R out and R2. Okay, so R out and R2 are in series, same current, which means that it has the same voltage drop. And also because V out is already defined in the original question, which is the negative terminal connected to the positive terminal of D2. So our negative terminal here, and if I redraw here R out and R2 in series, R out and R2 in series, take note of this voltage across R out, which is the V out, of the notation of the positive and negative terminals. Okay, so if I do a KVL around this loop, I'm gonna get minus V in, okay, a negative V in, minus V out, minus V2, which is also V out, which is equals to 0. So V out is going to be equals to negative 1/2 V in. So at the negative peak, where V in is negative 10 volts, okay, negative half of negative 10 is going to give me, V out is going to give me 5 volts. So if I draw the input voltage with respect to time aligned with the output voltage with respect to time, I can see that when V in is 10, V out is 5. When V in is negative 10, V out is also 5, and therefore I have this full wave rectification from the this configuration. And the DC average value is 0.636 times Vm, which is the maximum voltage of the output, which is 5 volts, not 10 volts. So 0.636 times 5 is 3.18 volts. So even though you're giving 10 volts, and because you have removed the 2 diodes from the original bridge rectifier, we see that the output voltage has now been reduced to 5 volts, and the average DC value is also not as high as 6.36 volt. It is half than that. It has become 3.18 volt. And the peak inverse voltage would be, for me to redraw this top part, to consider D2 to be in open circuit, okay, with the peak inverse voltage positive terminal indicated here, where it is the negative terminal of the diode. Okay, and I do a KVL around this loop, I'm going to get peak inverse voltage is equals to Vm, which is equals to 5 volts. Alright, so these are an example with the theory that has been described before. So after this lecture, go and read up the reference, do the tutorials, and you'll be in a better position to understand rectifiers. You will, when I prepared this lecture, a lot of these examples were taken from the Boylston text. Okay, text by Robert Boylston. Alright, so before I leave you, just some practical notes on rectifiers so that you don't imagine that these are just some theory that are written in textbooks but are not being practiced. These circuits are critical component in AC to DC power supplies. As I said, if you take it out from the wall socket before it goes into the television, in the television there is a rectifier circuit where a lot of these electronic devices you'll see have inbuilt DC power supplies, and it turns the wall outlets 120 or 240 volt AC signal into 3.3 volts, 5 volts, 12 volts, 24 volts, etc. Okay, so I took this from SparkFun. SparkFun is a nice place for you to go and learn on your own as a hobby, or if you want to pick up electronics at your own rate. You can have look at this website. Okay, and here you can see, try and spot the diodes. Okay, the 4 diodes that form the bridge rectifier, and this huge cylinder here is the capacitor. Okay, the same thing here. So you have here a transformer with the coils, the diode and the capacitor. I took this picture. This is a nice picture which I took from Shutterstock, royalty free, which shows a transformer AC power to DC power with diode, bridge and capacitor. Okay, some practical notes, more practical notes on diodes. So there are many types of diodes for a variety of applications. So you have diode for high power applications, and this diode for high power applications draw lots of currents, or they rectify high voltages, typically go by the name of rectifier diodes. It can go up to 1000 volts, okay, for ratings, meaning it can withstand those kind of voltages. But diodes that go by the names as signal, switching, fast recovery or high speed are designed to provide low internal capacitance. They're supposed to be fast diodes. They don't they have weak junctions, but they're good because when they don't store too much charge, they switch fast. So but rectifier diodes will need to be able to store a lot of charge, okay, without breaking down. So rectifier diodes are typically designed to handle high voltages compared to signal diodes. So if you buy these diodes online and you look at the data sheet, you can imagine that the values is going to be much higher. Okay, before we go off, so some practical notes on diode. You can look at diodes that are sold online. Okay, so it happens that I've included here a picture of which I've taken from RS Online Malaysia. If I put in diodes at the search box, I get 23,495 products found for diodes, and it can go anything from, oh, this is like not even 45 cents. This is 0.045 cents, about 5 cents, yeah, and all the way up to, so I did compare the prices. So this is one of the most expensive ones, which is an Infineon dual diode. So inside here there are more than one diode, and it costs right up to 1,500 ringgit, Malaysian ringgit. So these are all the examples that we have done for rectifiers, and I shall see you in the next video, which is going to be clippers and clampers. Thank you. Assalamualaikum.